All right, the first problem that people had difficulty with was number 4. Find the average value of the function f of x equals x cubed over the interval from 1 to 5. It's just a matter of knowing the formula and using the formula by applying the fundamental theorem of calculus. Some of you, it seems, maybe even many of you, didn't have the formula down, the right formula to use. This is not the average rate of change of something. So it's not a slope. It's an average value of a function. The general formula is to take 1 over b minus a, 1 over the length of the interval, and multiply that times the integral of the function from a to b. That's the general formula for average value. So in this case, f of x is x cubed, a is 1, b is 5. So we get 1 over 5 minus 1 times the integral from 1 to 5 of x cubed. Simplify, 1 over 5 minus 1 is 1/4. When you integrate, fundamental theorem of calculus says find an antiderivative. Some of you also made mistakes in finding the derivative instead of the antiderivative. And some of you just used x cubed still. Antiderivative of x cubed is 1/4 x to the 4th. So we get another 1/4 in there. This all gets evaluated from 1 to 5. Yes, you can multiply the 1/4 times the 1/4 to get 1/16. That's fine. 5 to the 4th minus 1 to the 4th. 5 to the 4th is 625. That's 625. 1 to the 4th is 1. So you get 624 over 16, which does simplify to 39, it turns out. Okay. So it's a matter of using the formula. As far as your future in calculus courses, if you take more calculus, I do want you to understand the meaning of this, and for that we'll use Mathematica. One meaning of it is this, the average height of the function. If I graph the function x cubed over the interval from 1 to 5, its average height is supposed to be 39. Now, that looking at this graph, it doesn't look like it's 39, does it? The lowest value is close to 0. F of 0 is in fact 0. Doesn't look like it's exactly 0, but oh, it's because I'm starting at 1. F of 1 is 1 cubed is 1. And the highest value is 5 to the 3rd, 125. The average of 125 and 1 is what, 63. But that's not what you do when you talk about the average value of a function. You don't find the average of the extremes. You find the height of a rectangle where the area under the graph is the same. So if I also graph a horizontal line at 39, the area under that graph of a rectangle is the same as the area under the blue curve. Why is this a good idea? Well, for example, if you were integrating if you're trying to find the average velocity, if f of x were an f of t and it were a velocity in meters per second, and you were trying to find the average velocity, if this were a velocity curve, it would tell you the answer is 39, say, meters per second. What that's telling you is if your velocity curve looks like this, meaning you're speeding up, if it's the blue curve, so you're going faster and faster over these 4 seconds from time 1 to time 5, the distance traveled is such that if you went at a constant speed of 39 meters per second, you would travel the same distance in that same amount of time. That's why that's a good idea for this to be the definition of the average value. It would correspond to your average velocity in that case. So a couple of you did something creative, and I gave you perhaps more points than I should have for being creative. You took the average values of these numbers, f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5, divide by 5. That gets you reasonably close, but it's not the exact right answer. That's like taking an arithmetic average. It's kind of like doing an integral by a Riemann sum, though not exactly, because if I were really going to do a left-hand sum, I'd really only want to add the first 4 and divide by 4. And if I were doing a right-hand sum, I want to do the last 4 and divide by 4. And that would be a better estimate for the integral. And we can go ahead and compute these things and see. So averaging these outputs doesn't give you 39, but it's not terribly far away from 39, and I think 45, yeah. If instead you average the first 4 of those and divide it by 4, that's like a left-hand Riemann sum. I guess it's further away. If you did the last 4 and divided by 4, that would be a right-hand sum. If you average those two numbers, I think we're probably reasonably close. That's a trapezoid sum. Whoops. 25 plus 56 over 2. Oh, got to get a decimal approximation. 40.5, not too far from 39. Okay. Number 5, you did pretty well on. Most people got number 5 right. However, I think I still probably want to put something like this on the final exam, but make it a little harder, perhaps. How? One way I could try to make it a little harder is emphasize a couple other facts that I did talk about in class a week or two ago, probably a week ago, but didn't come up on the exam. The fact that if f of x is even, so I'm not literally doing this problem right now, but if f of x is even, then the integral from negative a to a of f of x is 2 times the integral from 0 to a. You don't need that in this problem because we're not making any assumptions about f of x being even or odd. That would allow you to find this integral if you know that integral. It would also allow you to go the other way around. If you know this integral, you could find that integral because you could divide both sides of this equation by 2. I said that the wrong way. Writing it this way says you can find this one if you know this one. Dividing both sides by 2 says you can find this one if you know that one. So you should be able to handle it either way. If f of x is odd, then the integral from negative a to a, where a is any number, is 0. So I'm thinking I'm going to put one on the final exam similar to this problem, except you're going to have to use one of these facts as well. Okay. So again, most of you got this one right, but I'd like to also test you about these. These are pretty important facts. They come up in calculations all the time in Fourier series, which is real important in engineering. Signal processing, that kind of stuff is an example of applications of Fourier series. Doing these kinds of things, using these properties, really helps cut down on calculation, especially the second one, right? If you know the integral is 0 because the function's odd, you don't have to do any work. You don't have to use the fundamental theorem of calculus. Answer is 0, just like that. So those are pretty useful things. 6 you got, most of you got right. Some of you made some sign errors and that kind of thing. 6 is an important enough concept, though, that I may put this on the final. You're integrating the velocity to get the change in position. This is the velocity right here. That's an antiderivative. Find the change in position. Maybe I'd make it a little harder by not telling you the antiderivative. I told you that here, but maybe I'd make it so you need to figure it out. Yeah, I think I'll probably put this on the final. Most of you got it right. I'd say 75, 80% of you got this one right. You're integrating the velocity to find the change in position. If you got the antiderivative, you didn't even really have to write the integral, though it's not a bad idea to do so. You could just do the difference. But if you don't have a formula for your antiderivative, then you've got to figure it out. And so you should write the integral and figure out the antiderivative. So I think I probably will put this in the final, but you'll have to figure out what the antiderivative is. By the way, this is a polynomial example. There's nothing stopping me from changing a polynomial example to, for example, an exponential function. You know, maybe the velocity is e to the 2t. Let me write that better. E to the 2t. Maybe that's the velocity, and you got to figure out the change in position from time 1 to time 3. That's a little harder to integral to do, I think, for most of us. It's not super hard. But you got to practice this kind of thing. It's the fundamental theorem of calculus still. You got to guess an antiderivative of that. Okay, that would be 1/2 e to the 2t. Guess. Educated guessing. You know, it would be bad to guess cosine or something. It'd be bad to guess sine. It'd be bad to guess e to the 3t. The answer's got to involve e to the 2t from your knowledge about derivatives. You need the 1/2 in front because when you differentiate this, the extra factor of 2 comes from the chain rule. So this takes a little practice. If you've not done this much, you should practice it a little bit, make up your own examples. In this case, the change in position would ultimately be 1/2 e to the 6th minus 1/2 e squared, whatever that number turns out to be. And you could approximate. Maybe I'd make that a cosine of 3t or a sine of 5t or something like that. Practice some antiderivatives instead of just me telling you the answer. Okay? Taking notes about that to make sure you can do that. Make sure you practice some of those. Seven, I gave you some hints about, using L'Hopital's rule. A pure L'Hopital's rule problem, I wouldn't tell you, hey, that's an indeterminate form, but I was trying to re-emphasize things. I'd just say, find this limit. And you'd have to know, oh, that's an indeterminate form, so I need to use L'Hopital's rule. Most of you got it right. Though this was a fairly simple example. It's not the quotient rule. You take the limit of a new fraction where the new numerator, the top, is the derivative of the old numerator. The derivative of sine of 7x is 7 cos 7x by the chain rule. And the new denominator at the bottom is the derivative of the old denominator. The derivative of 3x is 3. That's now something that's continuous everywhere. This one's not continuous everywhere. You'd be dividing by 0 when x is 0. It's undefined at x equals 0, but the limit still exists. That's what L'Hopital's rule proves. This is continuous everywhere. You can evaluate the limit by plugging in 0. 7/3 cosine of 7 times 0. Cosine of 0 is 1. The answer is 7/3. Again, most of you did get this right. But maybe I'm creating the final exam as we go here. I might put a problem like this on the final, but not tell you to use L'Hopital's rule. And maybe you have to use L'Hopital's rule twice. You have to check and see if the new fraction is an indeterminate form or not. If it is, use L'Hopital's rule again. And hopefully by the second time, it's no longer an indeterminate form and you can plug in the number. Question?
If you did do it and it was no longer an indeterminate form, will you have to then take the quotient rule in order to find it?
No, you never use the quotient rule.
I know. Okay.
It's always L'Hopital's rule, or if it's not an indeterminate form, plug in the number.
No, I'm saying like you used L'Hopital's rule the first time and then it was no longer an indeterminate form. But it would, if you plugged it in, it would still be divided by 0.
Then the limit wouldn't exist.
Okay, cool.
Yeah. In some situations, the limit doesn't exist with indeterminate forms. Like if you're trying to, here's a simple example. If you're trying to find the limit of x over x squared as x goes to 0, you'd say, oh, that's a 0 over 0 indeterminate form. I guess I need to use L'Hopital's rule. Derivative of x is 1, derivative of x squared is 2x. That's not an indeterminate form, but it's also not something you can plug in 0. This limit doesn't exist. That function has a vertical asymptote at 0. What happens is, you can check this with your calculator. If you graph this function, it does on your calculator, it will look like it's got a value at 0 of 7/3, in fact. It will approach 7/3 as x approaches 0. I'm not exactly sure what the graph looks like, maybe like that. That's supposed to be a 7/3. But technically there's a point missing. There's a hole in the graph. It's not a vertical asymptote. It's a place where the function's undefined, but the limit still exists. That happens sometimes. And that's an essential thing in calculus, actually, because with limits of difference quotients for derivatives, that always happened as we let h go to 0. The resulting expression as a function of h always had an h in the bottom. It was technically undefined when h equals 0. It has a hole in its graph, but the limit still existed. So functions with holes in their graphs are not just curiosities. They are essential to deal with in calculus, even though we don't always talk about graphing. This one people either did fine on or really had no idea what they were doing. This is the parametric curve one. It was meant to be fairly easy. Using parametric mode in your calculator to graph it, you get a curve about like this. Some of you forgot to pay attention to the directions to indicate the direction of motion. That's this way as t increases. You want to draw arrows on these curves, it's not just the curve, it's the direction of motion. And it's even more than that, it's a speed, right? This motion, because the speed function is this function, you go faster and faster. That's the point, is you're modeling motion. This is not a graph of f or a graph of g, it's a graph of both of them combined. I didn't have you draw position vectors but when I put these kinds of problems on like Calc 2 exams, I typically have people draw position vectors. An arrow from the origin to the location of the object, that would be the position vector at time 2. I could write that as r of 2. And I also even have them draw velocity vectors. The velocity vector here, I didn't ask you about this, is a vector whose components are the derivatives of f and g. That's 2 and 2t. It's a function of t. When t is 2, v of 2, you get the vector 2, 4. Horizontal displacement of 2, vertical displacement of 4. The velocity vector looks about like that. It's tangent to the curve at this point. And as I showed you in the animations, these things change as you animate them, as the motion changes. The position vector and the velocity vector both change in magnitude and direction. Magnitude means their length, direction means what direction are they pointing. You can specify the direction by drawing a picture, by drawing right triangles like this. You can also specify the directions with angles if you like. Then you need to use trigonometry, though we never did that. As far as the speed function, that's just using the formula that the speed is the square root of f prime of t squared plus g prime of t squared. So I'm telling you what to do on this problem in case you had trouble. But I think I'm not going to put this problem on the final exam. There's f prime, there's g prime, so you do this. And I did want to see this kind of work. So if you just wrote the answer, that's not really doing anything because I told you the answer. There's the speed. It's a function of t. It's this graph. These graphs are not the same. They're related to each other, but they're not the same. This is a parametric curve, a function of t, which you don't see in the picture. It's just in your mind, in your imagination. Tracing out a curve like a bug walking along the page as time goes by. This is a graph of the speed of the bug as time goes by. Or maybe not a bug since it's meters per second, but maybe a person walking. This is the speed. The area under it is still the distance traveled. Even though it's two-dimensional motion, that's still true. It would be true even if it were three-dimensional motion. The area under the speed graph would still be the distance traveled. The three-dimensional motion would be all around through space. You'd need three components, a three-dimensional position and velocity vector through space, but we can still figure out the speed function as an ordinary function and graph it like this, and the area under it is still the distance traveled. They're not the same graph, but they're related. Notice the labeling of the axes is different on purpose. That's X and Y. This is T and speed. I could label this V if I wanted to, though don't get that confused with the velocity vector. This is not a vector, this is the magnitude of the vector. So I told you you could do the integral in two ways. You could either just use your calculator, or you could see that we're doing a right-hand sum to approximate. It does give you different answers, but either way you did it, I gave you full credit if you got the right answer either way, depending on the method that you used. As a right-hand Riemann sum, you do f of 0.5 times 0.5 plus f of 1 times 0.5. I'm using the right endpoints of each interval to figure out the areas of those rectangles, then I'm adding them all up. And yes, there is a 0.5 in each one, so you also could just add up the function values in parentheses, and then at the end multiply by 0.5. And sometimes people forgot the units. So I take off half a point if you forget the units. The units for this would be in meters. But wanted to reemphasize it, but I think I'm not going to put that on the final. Comes up in Calc 2 and multi, though. Especially in multi, you need parametric curves a lot in multi. And in differential equations for that matter, especially if you take difficulty with linear algebra with me. Parametric equations and curves come up all the time. 9, most of you got it right. So this is a graph of a flow rate in gallons per minute. This is a rate of change. It is a derivative, even though you don't see a prime. It's the derivative of a volume in gallons. And the point is that when you integrate the flow rate, you get the change in volume. Most of you got it right. You do the integral, so you do 3.8 minus 8.5 to get negative 4.7. Some people wrote positive 4.7. The answer is negative 4.7. And that does affect part B as well. If the initial volume is 12, how do you find the volume at time 4? You could say the volume at time 4 is the initial volume plus the change in the volume, but that change in volume is negative 4.7. 3.8 minus 8.5. I'm subtracting because I'm really adding a negative. And that gives 7.3 gallons. Probably 80% of you got this right. 10 was the one that very few people got full credit on. And it's not surprising, especially part B, I think. Even if you understood what was going on conceptually, part B was not so pleasant. If you got close on part B, if you got close, I gave you full credit, even if you didn't quite show all the details. Since it was hard enough as it was. Didn't make it a ton of points, part B, just 3 points in the exam. So I think I will put one like this on the exam, on the final. I'll change the function, but I'll probably still have 2 parameters. What are some different ways I could change it? Maybe I have ax plus b over x instead of b over x squared. Maybe I do an exponential function. Maybe I do like a times x times e to the negative bx or something like that, as an example of one that would be good to practice. Just said that verbally, you might want to write it down. A times x times e to the negative bx might be an example of a function where you're trying to find critical point and max or min value in terms of a and b. A times x, okay, I'll write it down. Ax e to the negative bx is another example that comes to mind. Or maybe ax plus b over x instead of b over x squared. Or maybe, I don't know how difficult this one is, ax squared e to the negative bx. Or maybe e to the negative ax cosine of bx. Yikes, that doesn't look so pleasant. Actually, this one's pretty important for some applications. Actually, all of these are pretty important for applications. These kinds of families of functions come up a lot in applications. This last one comes up in modeling harmonic motion with damping, like a mass in a spring going back and forth. And with friction, the motion slows down over time until you can't even tell it's moving anymore. The position is often given by functions like this. And what might be of interest is to figure out the first maximum. The graph would oscillate up and down. Where do you find the first maximum? I'm not quite sure how hard that one might be, though, offhand. Taking the derivative, you need the product rule plus the chain rule, and there'd be a messy equation. Set it equal to 0, solve for x. I'm imagining maybe tangent becomes involved, and maybe inverse tangent or arctangent. Go ahead and give it a try. I'll test it myself and see how difficult it is to decide if I put it in the final or not. Or maybe something different that I haven't written down. It'll be doable, though you'll need practice with these kinds of things to make sure you feel comfortable with them. Very important families of functions. So with the problem at hand, though, part A, show calculus and algebra to confirm the positive critical point is this thing. Yes, I labeled it x crit of A comma B, though I said you can ignore that if you want. Why did I do that? Well, I'm trying to emphasize that when you do this kind of thing, the results you get depend on A and B. They're functions of A and B. You could think of those as multivariable calculus functions of A and B. You could graph the three-dimensional graphs. Maybe we'll even do so here. As extra insight into what goes on here. It's a worthwhile thing to do. Same kind of thing with y min of A and B. So for part A, take the derivative. Another thing that I saw here with some people is they were making these problems much harder than they needed to be. I mean, sometimes people got stuck because, yes, it is a hard problem, but sometimes people got stuck because they just made their calculations way too messy. Keep it simple. It's if you're being super, super messy about things, probably you're doing something wrong. We can differentiate this with respect to x. You're looking at this formula here. The derivative of ax is just a, and the derivative of bx to the negative 2 is just minus 2bx to the negative 3. Done. That's the derivative. We want to set this equal to 0 and solve for x to find the critical point. Add 2bx to the negative 3 to both sides. X to the negative 3 is the same as 1 over x to the positive 3, so we get this. We want to solve for x, so I'll multiply both sides by x cubed and divide both sides by a. Then take a cube root. X is the cube root of 2b over a, and that is the same as 2 to the 1/3, b to the 1/3, a to the negative 1/3. That's what cube root means, is 1/3 power, or probably a better way to say that is that's what 1/3 power means, is cube root. That's the definition of 1/3 power. Now the harder part, part B. Use the answer from part A in algebra to confirm that the minimum value is this. And part of what's confusing about it is it's actually sort of easier to get this form of it first than it is this one. If you'd gotten just that, that's fine. I wasn't looking for you to necessarily write it that way. But if you understood the principle of what to do, I probably gave you at least 2 out of the 3 points, even if you just understood the principle but couldn't carry out the details. The principle is, there's your critical point. To find the minimum value, you've got to plug it into the function. Minimum value, the word value means output. Plug this into f. So I got to take 2 to the 1/3, b to the 1/3, a to the negative 1/3, and plug it into f. Probably using this formula here again would be a good idea. So I get a times x, so a times this. plus b times x to the negative 2 power. I got to take all this and raise it to the negative 2 power. If you got that far, you got 2 out of 3 at least. And then if you got closer, maybe I gave you 2.5 out of 3. And if you got really close and maybe didn't quite finish it, I gave you 3 out of 3 anyway. We're trying to finish this now. I said this sort of is easier to get. How? Well, continue simplifying a little bit. With this first expression, you can combine these a's. These are all multiplications, by the way. Right? There's no function. F is a function. I'm doing plugging in over there, but I'm not doing a multiplication. It's not f times that. F is a function, but now everything is a multiplication. So those a's can be combined by adding their exponents. This a is a to the first power. 1 plus negative 1/3 is a to the 2/3. Same as 1 minus 1/3. And with the next one, I've got to square everything. 2 to the 1/3 squared is 2 to the 2/3. B to the 1/3 squared is b to the 2/3. A to the negative 1/3 squared is a to the negative 2/3. Did I make a mistake?
Yeah, it's supposed to be negative.
Oh, yeah, negative 2 power. Yeah, I was feeling like something was wrong. This is a negative 2. So that's a negative, this is a positive. Sorry. And I said this is sort of the easier form to get. How am I going to get there? By getting a common denominator. Wait a minute, where are the fractions? Well, 2 to the negative 2/3 is 1 over 2 to the positive 2/3. So we want to get these things as something over 2 to the positive 2/3. This one already has 2 to the positive 2/3 on the bottom because there's a 2 to the negative 2/3 on the top. So there's what goes top is b to the first times b to the 2/3. Negative 2/3 is b to the 1/3. The a to the 2/3 stays as it is. Here I have to get this common denominator, so I've got to imagine multiplying this by a fraction, 2 to the 2/3 over 2 to the 2/3. Tracking with me here? I got to get that common denominator. I don't have any denominator there as is. Those are all positive powers. I'm going to multiply by 1 in the form of 2 to the 2/3 over 2 to the 2/3 so that I get a 2 to the 2/3 on the bottom. On the top, 2 to the 2/3 times 2 to the 1/3 is just 2 to the first. And these are now like terms. 2 to the 2/3 in bottom, and the tops are the same kinds of powers of a and b. I get 3 a to the 2/3, b to the 1/3 over 2 to the 2/3, which matches that. 2 plus 1 is 3. Got the same powers of b and a in the top and the same denominator. I just add those numerators. And yes, that does equal this, but that's a little easier to get. So if you got close, I may have given you full credit depending on how close you got. And then in part C, compute f double prime, explain why it's a minimum rather than maximum. The graphs must be concave up. That's what we're after, showing f double prime is positive. Again, some of you made it just too hard here. This problem, finding f double prime, is not as hard as some of you made it. Just differentiate this. F double prime is the derivative of f prime. A is a constant, so its derivative is 0. Derivative of that with respect to x, I bring down the -3. -2 times -3 is positive 6b x to the -4. So this simplifies to 6b over x to the 4th. And you don't even have to plug in the critical point. You can just say, oh, yeah, that's positive. It's undefined when x is 0. It's positive elsewhere. We're really focused on positive values of x. So that might be worth saying. So that essentially does it. I mean, the graph is concave up, and so it's a min. Some of you plugged in the critical point into that and got a mess. you didn't need to do so. So that was probably the hardest problem. Last page, 11 is a related rates problem. And again, some of you are just making it too hard. Perhaps because you just didn't know what to do. With implicit differentiation, and there probably will be an implicit differentiation problem on the final, and related rates, and yes, I think I will put a related rates problem on the final. The key is all on your perspective. With implicit differentiation, you have some equation involving x and y, where you have not solved for y explicitly. The equation, like the equation of a circle, for example, x squared plus y squared equals 1, does have a graph. The graph could be a circle or some other curve that might fail the vertical line test. It might not be the graph of a function. But near individual points, if you just look at tiny pieces of the graph, they could be the graphs of some function. So you assume that the equation defines y implicitly as a function of x rather than explicitly using some formula. And that assumption is the key to differentiating it with respect to x and realizing that whenever you differentiate y with respect to x, you get dy dx, not 0. Same kind of thing with related rates, except now everything's a function of t, time. Ruptured oil tanker causes a circular oil slick on the surface of the ocean. But this oil slick's not static. You got to use your imagination. It's getting bigger. Yes, that's bad. It's getting bigger. Actually, if all the oil is spilled out, it probably would be getting bigger radius-wise, but not necessarily volume-wise. It might be getting thinner on the surface of the water itself, but I won't go into details. At any moment in time, it's got a certain radius in a certain area. And there, of course, is the relationship between area and radius of a circle, A equals pi r squared. But these quantities are changing. They're both getting bigger. When the radius happens to be 200 meters, the radius is expanding by a rate of 0.3 meters per minute. At that moment, how fast is the area of the slick expanding in square meters per minute? So A and R are both functions of t. And when you differentiate this with respect to t, you need to keep that in mind. That's what you do. You differentiate with respect to t. What's the derivative of A with respect to t? It's not 0, because A is a function of t. Its derivative is dA dt. What's the derivative of the right-hand side with respect to t? It's not 0, because r depends on t. You got to use the chain rule. R is the inside function, R of t. Some of you assumed R of t was a linear function. And that could get you to the right answer, but that's a faulty assumption. This radius may not be expanding at a constant rate. In fact, in reality, it's probably slowing down over time. The radius probably expands pretty rapidly at first, and then as time goes by, the rate at which R is increasing slows down. The graph of R as a function of time is probably concave down in reality. Probably. I can't imagine it would be concave up. Could it be straight? I don't think it is. It could be wrong, I suppose, but you can't assume it. When you differentiate pi r squared with respect to t, you do not get 0. You get 2 pi r times dr dt. That's the chain rule. Only after you've taken derivatives do you plug numbers in. Do not plug the numbers in at the beginning. So now we take the derivatives. Now we can plug the numbers in. At the moment, the radius is 200. dr dt is 0.3. So there's the calculation to do. It's 120 pi. And it turns out to be, yeah, 376.99. Really, you would round that to 377.0 square meters per minute. But at some different moment in time with a different radius, the rt2 could be different as well. And the answer could be different. It probably would be better to use function notation to do problems like this. To write a of t equals pi times r of t squared. If you do it that way and get right answers, it's fine. In fact, I would say it's probably better. It's just more traditional to do it with the Leibniz notation. We're following tradition. Is it worthwhile to follow tradition? Yeah, probably, because it's what the physicists and engineers use. But if you're using function notation, you write it like that. Now, I don't know what time we're at where this occurs, but I can still plug the numbers in. It doesn't matter what time it is. We're at a moment in time where the radius is 200 meters and the rate is 0.3 meters per minute. Doesn't matter what t is. So once again, I'd still do the same calculation in the end, get the same answer. There's just a little bit more clear, you got to use the chain. So if you want to do it that way, it's fine. So I really put 2 optimization problems on this exam. For your final, there'll only be 1. It'll be more like 10 than 12. But you did have practical optimization problems without parameters here. And many of you knew what to do, but then made mistakes in your calculations. S is a function of x here. I could write f of x. You don't see an f of x anywhere, but I could. Tell you the truth, people are often sloppy here and will write something like that. S equals s of x, that's abuse of notation, but we live with it and we forgive and don't penalize when people do that, because kind of everybody does it except the mathematicians. Except when I'm teaching calculus and I'm doing it right now. Okay. Mathematicians are a little bit more picky about notation and not abusing notation like this. What is S? Is it a function name or a dependent variable? Well, it's both. A scientist would say, what's the difference? And I'd say there is a difference. Variables are numbers and functions are not numbers. They're functions, they're rules. Okay, so there is a difference, but it doesn't really make a difference as far as how you solve the problem. And so they would say, oh, I don't care, big deal. Right? You write h in terms of x, so you replace h with 200 over x squared. I'm not going to put a problem like this in the test, but if I were, I might, not even tell you this fact right there. You'd have to figure it out based on that fact. It's not hard to figure out. You need to realize you need to do it. And some of you tried to use, like, we're looking at this and said, oh, I guess I gotta use the product rule and or the quotient rule. But no, you can simplify it first. One of those x's cancels. And for differentiation, it's better to write it like this. So it's not too different from number 10. Set it equal to 0 again. Thank you. Let's see. Yep, negative 2. Thought something seemed wrong again. Thank you. 2x equals 800 over x squared. Just rearranging. So x cubed equals 800 over 2 is 400. X turns out to be cube root of 400. You use your calculator. It's like 7 something. 7.37, yep. And then just make sure not to forget units. Centimeters? Yeah, centimeters. And then H can be found from the constraint. H is 200 over x squared, and if you plug this in, you get about 3.68 centimeters. Actually, because of rounding, this is not obvious, but it turns out that H is exactly half of x. It doesn't look that way because of rounding. But in this problem, it turns out that H is exactly half as big as x for a fixed volume. And that holds in general. If you got a cylinder with a fixed volume, the minimum surface area this is a box, not a cylinder. You get an open box, so the top is missing. It's not a cylinder. You got a fixed volume. What's the minimum surface area? It'll turn out that no matter what your volume is, the height will be half as big as x. So it'll be sort of a short box. Height is half as big as the base.